2.9, these are the related rates problems. And we know that because if you look at all of your units, like it's like per something per second. You know, we see those derivatives in terms of rates. So on number 3, it says the width of a rectangle is half the length. Okay, so we know rectangle, you have length and width. I said the width is half the length, so you could call that half the length. But if we start looking at the other information, it wants to know at what rate is its area increasing. What did I always tell you guys to do on these problems? Yeah, but I made you like go out to the side and write down all the stuff you had. If I want the rate, that's a derivative for the area. It's a rate, so it's a derivative in terms of time. So the dA dt is what we are looking for. At the instant when the width is 10, can I just make my width 10 in the problem though? No, because it's changing. It's not always 10. The only numbers you can plug in at the beginning are the ones that never change. And the width is increasing. So I'm telling you how the width is changing. So that's dw dt. It's increasing, so it's a positive 0.5 centimeters per second. Okay, quick check. We have centimeters per second, so our units match. My information is all about w, so I really don't want to call my width half the length. I don't want else here. So if the width is half the length, what could I call my length? 2w. If I'd given you like dl dt, then we would have kept the length here. All right, so we have things kind of set up. We're talking about area. How do you find area of a rectangle? Length times width. So 2w times w is 2w squared. All right, we need a derivative. So we're doing a derivative in terms of time. So everything gets a d something dt with it. So derivative over here would be a 4w, and that was in terms of time, so dw dt. Then we plug in what we have. So my w is 10, dw dt is 0.5. So 4 times 10 times 0.5 gives us 20. And then my units. The top was area. What kind of units does area have? Okay. Divided by is a per, and then the time was measured in seconds. So the area is increasing 20 square centimeters per second. Is that one okay? Problem 4. A plane is flying horizontally at an altitude of 1 mile and a speed of 500 miles per hour. So the altitude is not changing because we're flying horizontally. So I can go ahead and call that 1. Now my plane is flying along. So what would I call this? We need a variable. So pick a letter, x. If I'm telling you miles per hour, what does that represent? The rate. So that's the derivative. dx dt is 500. And it passes directly over a radar station. Find the rate at which the distance from the plane to the radar station is increasing. So here's my plane. At some point it flew over a radar station and kept going. So now we have a distance between them. So again, that's changing, so I'm going to call it y. I want the rate that's changing, so I'm looking for dy dt. At the instant when it is 2 miles from the station. So at the instant when the y is 2. So when we have triangles, what formula do we use? So x squared would be plus 1 squared, the derivative of that would just be 0, equals derivative of y squared would be 2y dy dt. Right. I don't know my x. I know dx dt is 500. Y is 2. I don't know dy dt. So the problem is right now I still have too many variables. Dy dt is what I'm trying to find, but I have to know my x. So how am I going to get that? If we go back here, we can do 1 squared plus x squared. We need x at the instant when the y was 2. So x squared is 3, so x is the square root of 3 at that particular instant. Right? So then we have 1,000 radical 3 equals 4 dy dt. So dy dt is 250 radical 3. Units. Y would be measured in miles. Her time on this was measured in hours. So 250 radical 3 miles per hour. Any questions there? So problem 5. Water is leaking out of an inverted conical tank. So we have an upside down cone. This was actually a homework question at one point. And water is coming out of it at a rate of 10,000 cubic centimeters per minute at the same time that water is being poured into the tank at a constant rate. So water is coming in, I don't know how fast, we could call that a constant, and then water is coming out at a rate of 10,000. When you say cubic, what am I talking about? Volume, and centimeters per cubed per second, so that's dV dt. What would be my overall change in volume? The rate it's coming in minus the rate it's going out. All right. The tank has a height of 6 centimeters. So that's my overall height here. Make sure all of our units match. So far everything is in terms of centimeters, so we don't have any concerns there. The diameter of the top is 4, so that means the radius would be 2. If the water level is rising at a rate of 20 centimeters per minute, what would that be? Any rate is something in terms of time. It's talking about the height. It's rising, so it's a positive. At the instant when the height is 2 centimeters. Find the rate the water is being pumped into the tank. So we're looking for C. We're dealing with volume here. Volume of a cone is 1/3 pi r squared h. Here's the problem. If I do that derivative right now with the r and the h, we have to do a product rule within that. So it's going to become complicated, and I would get a dr dt. Do I have any information about dr dt? No. So I need to get rid of my r before I do my derivative. So that's where this other information comes in. 2/6. That is the ratio of the radius to the height. So if you wanted to solve for r, 2/6 is 1/3 multiplied over the h, so the radius is 1/3 of the height. So we're plugging that in before we do our derivative. Okay, so 1/3 pi, that's pi over 3. Radius 1/3 h squared times h. 1/3 squared is 1/9 times pi over 3 would be pi over 27. H squared times h is h cubed. So then what would we do? Derivative. So derivative of v would become 3 comes down, so 3 pi over 27 is pi over 9. H squared, derivative of h would be dh dt. Plug in what we have. So dv dt is c minus 10,000 equals pi pi over 9. H is 2 squared. dH dt is 20. And so we get 4 times 20, so 80 pi over 9. So C is 80 pi over 9 plus 10,000. If it were the final, I would want you to just leave it like that because we're trying to avoid the calculator. There is no need to plug that in the calculator if we're on final. If you did, you get something like, if you're trying to check yourself, it was like 10,027.93. But the other thing we need is units. C was the rate it was coming in, so it was a volume. So volume is cubic centimeters in terms of time, which was minutes. Is that okay? Okay, are we feeling better about the rates? You just have to realize if I'm talking about how things are changing over time, that's when everything gets a d something dt with it. Right. Then our next question, problem number 7. Use a linear approximation to find the square root of 102. So the idea is some things are hard to calculate, okay, but we know that we could find a tangent line. And if you're somewhere on this curve close to the tangent line, your value is close to the point on the line. That's what a linear approximation is. You're using a line to approximate the value. So if you're going to do it, you need a function and a point. So my function, what am I trying to do? A square root. So square root of x is my function. Now my point, I'm trying to approximate 102, but that's not a nice point. What is something close to 102 that we could do the square root of? 100. All right, the y value of that point. If you do the square root of 100, you get 10. All right, so here's a point. If you're going to write the tangent line, you need a point and a slope. How do we get the slope of a tangent line? Okay, we have to put our x value into the derivative. So our derivative, like x to the 1/2, so 1/2 x to the negative 1/2. So that's like 1/2 square root of x. So to get my slope, we plug in our x. Square root of 100 is 10, so our slope is 1/20. Now we have a point and we have a slope, so we use them to write the equation of a line. So y equals m times x plus b. So the y-intercept is 5. So we usually, instead of y, call it L of x just for linear approximation, is mx plus b. So this is the line we could use to approximate our square root. So now I wanted you to approximate 102. So if we put in 102, okay, 102 over 20, that reduces to 51 over 10. 51 over 10 would be 5.1 plus 5, 10.1. So the square root is approximately 10.1. Is that one okay? Problem number 8 is related to this. We were talking about differentials. The idea behind differential is we know that tangent line is not exact. So it's basically finding how far off are we if we use this. We have that our y is equal to the square root, or 3 plus x squared to the 1/2. Okay, if I want the derivative, and I know I need a derivative because I'm asking you to find dy. So derivative of y, we can call that y prime. We can also call it dy dx. 1/2 comes down. Inside stays the same. Subtract 1 from the power times derivative of the inside, which is 2x. So dy dx. 1/2 times 2x would just be x times 3 plus x squared to the negative 1/2. But if I want you to find dy, how would you get rid of the dx? So dy equals, I told you in the problem that x was 1 and dx is negative 0.1. So 4 to the negative 1/2 means 1 over the square root of 4, so 1/2 times negative 0.1. So like 0.5 times negative 0.1 would be negative 0.05. Questions there? On problem number 9, do we need A or B? How do we find maxes and mins? What do we have to do? Derivative. Critical points are anywhere the derivative is 0 or undefined. And then how do you determine the max and min from those? Yep. You plug the critical points along with your endpoints into the original function. The highest y value is your max, the lowest is your min. So if we look at 9c, we had that the function was x plus the absolute value of 7 minus 3x. All right, the problem with this is the absolute value. I've told you all along, we can't do derivatives or anything if it has an absolute value, so we have to rewrite it without. Think about what an absolute value does. The graph is a v, right? If you're looking at a v, we know the derivative is undefined at that point. So that point is when the inside is equal to 0. So that's when my x is 7/3. So I already know that 7/3 would be a critical point because that's where the derivative will be undefined. To find the others, we have to rewrite our problem. And we always did it as a piecewise function. So we have one case if x is less than 7/3, and one case if x is greater than 7/3. We don't have to worry about equal to because we already know that's the critical point. If you plug in a number smaller than 7/3, so if I put in a 0, then the number in the absolute value is positive. Does absolute value change a positive number? No. So that just simplifies to 7 minus 2x. If you put in something bigger than 7/3, so maybe like a 4, then what happens to my absolute value? It's a negative, and the absolute value would make it positive, so it does the opposite of this. So that's like negative 7 plus 3x, so we get 4x minus 7. So that's how we rewrite it without the absolute values. Are we okay there? All right. So our derivative, we do the derivative of each piece. What's the derivative of 7 minus 2x? Negative 2. What's the derivative of 4x minus 7? 4. Critical points are anywhere the derivative is 0 or undefined. We have the undefined, now we look for the 0. Does negative 2 ever equal 0? No. Does 4 ever equal 0? No, so if the derivative can't be 0, this is my only critical point. Our interval was 1 to 5, so make sure we're on the interval, and we are. So we have to test all of these. These are going back into the original. So if you put in a 1, you get 1 plus the absolute value of 7 minus 3. So 1 plus 4 is 5. Oops. If you put in a 7/3, you get 7/3 plus 7 minus 7. So that would be 0. So we just get 7/3. If I put in a 5, I get 5 plus the absolute value of 7 minus 15. So the absolute value of -8 is 8, plus 5 is 13. So this is my highest, that's the absolute max. This is my lowest, that's the absolute min. Or global maximum, they could be same term, maybe, or different terms mean the same thing. All right, is that okay? So problem number 10, talking about mean value theorem. Okay, mean value theorem and Rolle's theorem start out very similar. Mean value theorem says that if your function is continuous and differentiable, then somewhere on the interval, the derivative is equal to the slope between the endpoints. Rolle's theorem is like a special case of mean value. It has to be continuous, it has to be differentiable, and the endpoints have to be the same. If the endpoints are the same, what's the slope between them? 0. So then Rolle's theorem says somewhere the derivative equals 0. Alright, so first you have to verify your criteria. This is a polynomial. So it's automatically continuous. And it's actually continuous everywhere, but it only has to be on our specific interval. Second, it's a polynomial, so it's differentiable as well. And again, it's differentiable everywhere. The requirement is just that it has to be on the open interval. So I was pretty lenient with verifying the criteria on those. If you just said it's a polynomial, so it's continuous and differentiable, that's fine. But you do have to acknowledge that, because if it's not, if we have something with a break in the graph, then the mean value theorem doesn't have to work. All right, so then mean value theorem says the derivative is equal to the slope between the endpoints. So let's talk about our endpoints. Our x's are 0 and 2. If I want to order pairs, we have to plug those into the function. Okay, so if you put in 0, you get 2. If you put in 2, you get 8 minus 6 plus 2, which is 4. The slope between those, y2 minus y1 over x2 minus x1 is 1. So then our derivative has to equal 1. Is everybody with me so far? So solve this equation. So 3x squared equals 4. So x squared is 4/3. Square root plus and minus. Square root of 4 is 2 over the square root of 3, or 2 radical 3 over 3. Would I use both of those? Why not? I only want the ones that are between 0 and 2. So the only value that works on our interval is the 2 radical 3 over 3. Is that okay?
So we have to check and see if our slope is the same as.
Well, if the criteria are met, so you have to check the criteria. If those criteria are met, then this has to work somewhere between 0 and 2. The slope will equal that derivative. That's what the mean value theorem tells us. So you check your criteria, and then you know there will be a point that makes it true. And Rolle's theorem has the same first two criteria. Then the third criteria for Rolle's is that what? The endpoints are equal, and then there's a point when your derivative is 0. All right. Problem number 13. So 12 and 13, these are the long problems. So this will be like 1 page will be this question. So, oh, you know what 1 whole page of your test looks like. We have to be able to go through all of these and get an accurate graph. And remember, everything I have you find, I am expecting you to plot on your graph. We don't find it just for fun. We're putting it on the graph as we go through. So, first thing on this one, because it's a fraction, we know we have asymptotes. Vertical asymptote. Our x equals anything that makes the bottom 0. If you set the denominator equal to 0, you get x squared to be -4. What kind of numbers are we getting? Imaginary. So that means there is none. Okay, how do we find the horizontal? As x goes to positive and negative infinity. Okay, if I just plug that in right now, it's infinity over infinity. That doesn't help me. So what do we have to do first? 1 over the highest power of x. So we'll take top and bottom times 1 over x squared. So I get 1 minus 4 over x squared over 1 plus 4 over x squared. And we know a number over infinity goes to 0, so that just goes to 1 over 1, which is 1. So our horizontal asymptote, it is a line, so you have to give me the equation, y equals 1. Okay, so I've got that part. Next thing on my list, critical points. So how do we find critical points? Derivative equal to 0. So I have to do quotient rule. Low d high minus high d low over low squared. So if we multiply that out, we get 2x cubed plus 8x minus 2x cubed minus 8x in my denominator. We distribute the negative, those cancel, 8x plus 8x, 16x over x squared plus 4 squared. So, we need to know where this is equal to 0 or undefined. Undefined would be when the bottom is 0, and we've already established that that was imaginary. So this is just if you multiply over the bottom when 16x equals 0, so that means x equals 0. So that is our critical point. How do I check to see if it's increasing or decreasing? We're checking the sign of the derivative. So we do test points. We're putting them into the derivative. So if I put in a -1, I get a -16. The bottom's squared, so that's positive. A negative over a positive is always negative. If I put in a +1, we get positive over positive, which is positive. So we know we are increasing from 0 to infinity, decreasing negative infinity to 0. So does that make 0 a max or a min? You go from down to up, that is a min. And I want an ordered pair for that. How do you get the y value? The original. So if I put 0 back into my original equation, we get -4 over +4, which is -1. So 0, -1 is a local min. on my graph. All right, how do we find inflection points? Second derivative equal to 0. Okay, so low, d high, derivative of 16x is 16, minus high, d low. So 2 comes down, inside stays the same, subtract 1 from the power times derivative of the inside. Over low square. So if it's squared and you square it again, it becomes to the 4th. What can we do now? Let's make life a little bit easier. Take out one of these. So if we distribute, we get 16x squared plus 64. Okay, over here I'm taking 16x times 2 times 2x. So when we do that, get negative 64x squared. And for the denominator, so 16x squared minus 64x squared is negative 48x squared plus 64 over the bottom. Anywhere this is 0 or undefined. We already know it's not undefined because we've had the same denominator the whole time. We know that's imaginary. So we really just need to know what makes the top equal 0. So 64 over 48. That can reduce. We divide them by 16, 4/3. So square root plus or minus 2 over the square root of 3 or plus or minus 2 radical 3 over 3. So we have 2 inflection points. We need our concavity, so we put these on our sign line. Something between them, so maybe a 0, something to the left and right. So maybe like a negative 2 and a positive 2. So if you put in a negative 2, top, negative 48 times 4 plus 64, that would be a negative. Negative 2 squared becomes positive, so the bottom's positive. So that gives us negative. Put in a 0, we get 64 over 4 cubed, so that's positive. Put in a 2, the top is negative, bottom's positive, so we get negative. So we are concave up where we are positive, which is in between these. We are concave down elsewhere. All right. So now we have found all the stuff I asked for. We need to plot it all on our graph. So our inflection points, what do I need to be able to graph those? Ordered pairs. What am I plugging them into to get the ordered pairs? The original, because I need the point on my actual graph. So if we put those in, if you square them, you get 4/3. What do you get? I don't have a calculator handy. 1/5 and -1. Or they should both be. Yeah. Okay, so if I plot those, we're going to approximate a little bit here on our graph. So negative 2x over 3, negative 1/5. We marked inflection points with x's. So we know that our graph has to start off decreasing and it ends increasing. So we're falling, we're rising. We know an asymptote is something we're getting close to but not touching. Our graph is starting out falling but curving downward. Falling, curving downward. Here we're going to make a slight change to curving upward. Staying curving upward. We're increasing now, and then we need to switch back to curving downward. So it should look like that. Alright. We'll get through as many of these as we can. We have a smaller chunk tomorrow, so we should have time to go through all the extra. The limit. So 15b, we have the limit. We approach 0 from the right. Are you guys okay on the last question? I should have clarified that before I moved on. So those graphing ones, that's worth a ton of points right there. That one question could easily be worth anywhere between 20 and 30 points. So make sure you know how to do those. It's a big part of it. All right, so if I ask you to do this limit, we check. If I put it in, we have 0 times, if you think about a natural log, remember the graph looks like this. So it's 0 times a negative infinity. Can we do 0 times infinity? No, this is an indeterminate form. L'Hopital says it has to be written as a quotient before we can do that. Now you can't just like divide them, it has to be equivalent. So what we always did is put the reciprocal on the bottom. Because to divide fractions is the same as multiplying by the reciprocal. So that's equivalent to our original. Okay, the top, the natural log of 0 from the right is still going to negative infinity, but now the bottom is also going to infinity. So infinity over infinity says we can do L'Hopital's. And I asked you to label when you did it. L'Hopital says if it's infinity over infinity or 0 over 0, we can do the derivative of the top over derivative of the bottom. Derivative of a natural log, 1 over the argument. Okay, 1 over x, that's the same thing as x to the negative 1, so its derivative would be negative x to the negative 2. So that's like 1 over x over negative 1 over x squared. Okay, this looks ugly, but how do we divide fractions? If I do that, I get, when it's x approaches 0 from the right, of negative x, which is just 0. C. Okay, this is currently 0 to the 0 power. Can we do it? No. We can't do L'Hopital's unless it's 0 over 0 or infinity over infinity. So what did we do on these problems? Added a log. The reason we liked the log is because properties of log say your exponent comes down in front. And if I add a log, that means my answer is going to be e to the power. We need the e to cancel the log. Okay, currently it's 0 times infinity. We can't do that, but just like the last one, we can make it a quotient. We don't want to move the natural log, but I can move the square root of x to the bottom by making it x to the negative 1 half. So now we have infinity. So now we can do our L'Hopital. Still writing our limit on every step because we haven't calculated it. The derivative of natural log is 1 over the argument. At the bottom we would have negative 1 half x to the negative 3 halves. Try to clean up after your L'Hopital's as much as you can. Usually when your problems get really ugly, that's because you fail to simplify something. So this is like negative 1 over 2x to the 3 halves. So we can flip and multiply. Alright, so we have a negative 2. When you're dividing, you subtract exponents, so x to the 1 half. So if you put in 0, negative 2 times the square root of 0 is 0. So our answer is e to the 0 power, which is So far, so good? I'm going to jump down to 21. Just trying to do problems that I know I can get done before the end. Okay, what does A of t stand for?
Acceleration function.
What am I asking you to find?
Position function.
Position. So we need to do the antiderivative. We know in general, your position, derivative of position is velocity, and acceleration is the second derivative. So we're starting down here. If I do the antiderivative once, I will get my velocity. So the velocity, antiderivative of 10 would be 10t minus 15t squared. What do we need on the end? Okay, but I gave you some information to find c. I said v of 0 is equal to negative 5. That means if you plug in 0 for all of your t's, we get negative 5. So c is negative 5, so my actual velocity is 10t minus 15t squared minus 5. So if I do the antiderivative again, I will get my position. Antiderivative of 10t, antiderivative of 15t squared, antiderivative of 5 is 5t, and then we need plus c. So now we need our constant, but I told you the position at 0 was also 5. So if you put in zeros for all of these t's, it equals 5, so the constant is 5. So our actual position function is 5t squared minus 5t cubed minus 5t plus 5. And you could certainly reorder those terms if you preferred. Okay. I don't think I have enough time to finish one of the others if I were to start it, so I will go over those 3 tomorrow, as well as anything you have from the second half. So make sure you finish it. Hopefully this section part goes a little faster because it's more recent stuff. And then tomorrow, if there are more questions we need to add to the list, we will. And if we end up with extra time, I'll have some other problems that we can